section we're going to take a look at, a couple sections, is on what we call polar coordinates and complex numbers. So the first part of what we're going to look at is section 5.1. The last part we're going to look at for the week is 5.3. And then in the middle, we're going to look at section A4. A stands for appendix. It's a section that's in the back of the book, and it's kind of like it's the connection between 5.1 and 5.3. It's something you did in Algebra 2, complex numbers, but I think it's good to go over it again, just in case people don't remember that from last year. So the kind of graphing that we've done, like when we graph sine and cosine, or when we've done coordinates on the unit circle, is the kind of graphing system that uses this. Right? You have a vertical and a horizontal axis, x and y. And to find a coordinate somewhere on here, you write down two numbers, usually an x value, comma, and then you put a y value. And that type of graphing, or that system, is very good if you want to draw things that are straight lines. Okay, if you remember from Algebra 1, y equals mx plus b, super easy to graph lines in that system. What that system is not easy to use for is circles, or anything that's curved. Okay? Things that are curved, especially circles, are much easier to do in a different system. So I'm going to show you on a graphing calculator how I could draw a circle in this system. And then I'm going to show you how I can draw a circle in what's called a polar system. And you'll see how much easier it is in polar. Okay, you don't need a graphing calculator. I'm just going to show you something on it, but again, it's not something you need for this week. Let's get to that. First of all, if I want to draw a circle in this kind of system, I can't, technically. I can only draw things in this system that pass the vertical line test. Vertical line test is when you draw something, you put a vertical line, and it only hits it in one spot. Well, with circles, it doesn't work. Circles, it hits it twice. So the only way I can draw a circle in this system is to kind of cheat and do the top half of the circle, and then separately draw the bottom half. That's the only way I can really do it. Right, so I'm going to type that in and show you what a circle looks like. Now I have to pick what size circle I want to do. I'm just going to do one with a radius of 3. Okay, so it'll have a diameter of 6. I could do any size I want. All right, so to graph a circle, I have to type in, and I'm going to show you this whole thing that I have to type in. We're doing a radius of 3, so let's type in this. And if I do what I just typed in, I'm going to show it to you. You can see what I get there is the top half of a circle. And to get that, I had to type in that. Now I'm going to do the bottom half. So I'm going to type in, again, you don't have to know the equation. I just want you to see how much stuff I have to type in to draw a circle. And that's the bottom half. And it doesn't even really connect, but that's the best I can do. Okay, on this kind of calculator, that's all you can do. So here's everything I had to type in just to draw a circle. All that stuff. That's using an XY coordinate system. Now, let me show you how I can do the same thing in polar. And I'll show you everything I have to type in. So I'm going to switch my calculator to polar. I'm going to type in one number. I'm going to hit graph. And oops, I didn't turn it on. Let's go 0 to 60. And that's it. So to get a circle using a polar coordinate system, all I had to do was type in a single number. Typing in a single number is a lot simpler than typing in all that stuff. And this graph looks a lot better because it actually looks like a circle. All right. So I just want you to see how much less stuff you had to type in polar to draw a circle. Now, if you wanted to draw a line, this is not a good system to use, polar. Lines become very complicated in polar. What's the best way to draw a line? The way you already know, the y equals mx plus b. We're not even going to get into drawing full graphs in polar. You can do circles, you can do spirals, you can do all kinds of different shapes. But what we're going to be looking at is just graphing single points. Okay? That's it. Okay, just single points. And the system that we use to graph things in polar doesn't have an x and y axis. It really only has one axis. Okay, that's called the polar axis. And instead of it being like rectangular square shapes, like when you have a grid like the one that's behind here, it's not square shapes. The grid, or the actual graph paper, would be concentric circles, okay, coming out from the origins. Okay, so that's an example of what polar graph paper looks like. Want to see another example? There's another one. A lot of times what they'll do is they'll draw in these radial lines from the center. And each one of those lines is going to represent a certain amount of degrees. On this one, there's 6 lines in each quadrant, so it separates it into 15-degree increments. This is 0, 15, 30. The red lines are the 45s, 60, 75, and then 90 is up top. Okay, the polar axis is horizontal, and the center, you can call it the origin, but it's also called the pole. Now, what I would do is, if you're doing for homework, if you don't have a piece of polar graph paper, and you don't want to have to sketch a polar graph several times, just sketch one graph and just label your problems. Like, that's number 2. That's number 4. Just label which one is which. Then you don't have to draw the same thing over and over. If you want to print out a piece of polar graph paper, you could. I might have some. I can double check. But you're not going to need to draw it more than once. Yep.
Do we have a test on this Friday?
Yes.
Because it's senior skip day.
Oh. I don't know. So that's your graph. Okay. We're going to just start by graphing single points. Now, when you graph a polar coordinate, it doesn't use an x and a y value. It uses an r and a theta value. Okay, those are the 2 different values. Now, we're graphing things on something that's a circular kind of grid. So what do you think R stands for? Radius. Yeah, R is radius. And theta usually represents what? Or what do we always use a Greek letter for? Yeah?
Angles.
An angle. So when you graph something in polar, you might have already seen it when I click to this next page, that's what a point looks like in polar. It's not an x and a y value. It's an R and an angle. It's a radius and an angle. So there's really a couple different cases we can look at, and it's the same thing you'd look at when you're graphing an xy coordinate. You have to look at whether x and y are positive or negative, and that tells you whether you go left and right for x or up and down for y. Well, same idea here. We're going to look at if r is positive or negative. That's going to tell you something. And then we're going to look at if theta is positive or negative. And that's going to tell you something else. Okay, so the first thing you look at is r, just like in an xy coordinate. Look at the first number. And r is it's kind of like x in terms of what you need to do. You're going to move out from the pole, from the center, the number of rings indicated by R. There's two ways you can move out from the center. You can either move to the right or you can move to the left. If R is greater than 0, you're going to start by moving to the right. So if R is greater than 0, you're going to move to the right. How far to the right? Well, it depends what R is. If R is 3, move 3 to the right. If R is 6, move 6 to the right. It could be a decimal, 2.5. So move 2.5 to the right. Which way do you think you would move if R is negative? To the left. And you move to the left however many units it tells you to move. Now, just like when you graph an XY coordinate, that's not the final answer, that's just the first number. So you move left or right. Now we're going to look at theta. So after you do step 1, which is moving left or right, now you look at theta. Remember, theta represents, what's theta again? It's an angle. Angular movement is on a circle. When you move on a circle, we don't use up, down, left, and right usually to describe rotation. What are the two directions you can rotate in? Yep.
Clockwise and counterclockwise.
Clockwise and counterclockwise. And depending if theta is positive or negative, you're either going to go clockwise or counterclockwise after you do step 1. So you do step 1, how we just explained it, and then you look at your angle. If your angle is positive, you're going to move counterclockwise from where you ended up after doing step 1. If the angle is negative, you're going to go clockwise. So those are the two directions that you can move on the circle. Counterclockwise is this way. Clockwise is this way. The next 5 or 6 problems we're going to do is just practicing graphing the point. Okay, so, any questions on the two directions you can go? When you go clockwise or when you go counterclockwise? All right, let's try an example. Bless you. All right, so here's our first one. The point is 3, 120 degrees. Now, this isn't a graph of an entire shape. It's not going to be a circle or a spiral. It's going to be a single point. That's as fancy as we get, just single points. All right, so we're going to start with the 3. And how about Dylan? When I look at the 3, that's my, which one, my radius or my angle?
Your radius?
My radius. And that means we're going to go 3 units which way?
To the right.
To the right. So we're going to start here. I'm going to erase that mark in a second, but that's just a temporary mark so I know where to start for step 2. So we're going to start 3 units to the right. Yeah, I'm going to erase that. And now from there, we're going to rotate a certain amount of degrees. Devin, how many degrees am I going to rotate?
120.
I'm going to rotate 120, and it is important we get the right way. So Tyler, are we going to go clockwise or counterclockwise? Counterclockwise, right? Because that's a positive. So positive goes counterclockwise. Each one of these lines is 15. If we go up to the top, how many degrees have we just rotated? 90. And how many more do we have to go to get to 120? 30 more. Each one of these lines is 15. So that's where you would end up. So that's right 3, and then rotate 120 degrees counterclockwise. That's how you graph wing and polar. Questions on it?
So is it just the points?
It's just the point. Yep. It's just a single point. If we were going to spend another day or two on it, then we'd get into graphing things like spirals and circles, and cardioids, and all kinds of other shapes. All right, let's look at this one. 5 comma pi over 4. What's different about the angle this time? Yeah. It's in radians. If you want to change it to degrees because you find that easier to work with, you can. If you can work with it in radians, then just work with it in radians. I'm going to guess most people want to probably put it in degrees. Does anyone remember what pi over 4 is in degrees? Yeah? Yeah, good. It's a 45. Again, that step isn't necessary. If you can do it in radians, do it in radians. Okay. Brian, what am I going to do to start graphing this one?
You're going to start with 5.
Yep. And we're going to go 5 units which way?
To the right.
To the right. Now again, going 5 to the right, that's not the final answer. That's just the first part. So we're going to go 1, 2, 3, 4, 5. Now, from that spot, which I'll probably erase in a second, I need to rotate a certain amount of degrees. Haley, how many degrees are we going to rotate? Yep, so we're going to rotate pi over 4 radians, which is the same as...
I don't remember how many degrees. 45.
45. So it's the same as 45. Now we got to make sure we go 45 the right way. Tyler, which way are we going to go for 45 degrees?
Counterclockwise.
Yep, counterclockwise. Each one of these lines is 15. So we're going to go 3 of them. 15, 30, 45. And that's it. And that's your final answer. Any questions on how we graph that one? So, still pretty similar to the first one. Radius was positive, and the angle was still positive even though it was in radians. Let's try one where we have a negative. So this time my radius is 5, and my angle is negative 210. Allie, what's going to be my first step to graph that?
We're going to start with the 5 radians, which going at 5 rings.
We're still going 5, yeah, which way?
To the right.
To the right. So that is your starting point for the next step. 5 to the right. And Ryan, how many degrees are we going to rotate?
Negative 210. So 210 to the left. Counterclockwise.
So we're going to rotate 210. And which way for a negative?
Counterclockwise.
That's for a positive.
Okay, so clockwise.
We're going to go clockwise. So we need to go clockwise 210. So clockwise is going this way. So if we go halfway around, how much is that?
180.
180. And we still got to go 30 more to get to 210. So that would put me right there.
Okay. I was thinking it would be turning the whole graph. Like, it's hard to explain. I was thinking more the wheel spins, and then you're trying to line it up at 0 rather than you actually moving around.
Yeah, so that, the background, imagine that staying still.
Right. Okay, I understand how that makes sense.
So we go 5 to the right, and then 210 degrees counterclockwise. On the test, you'll have to do some graphing just by clicking where you want to put a point. There'll be a background, just like this on the test. I mean, it might go by 15s. There might even be more lines, because you can go by, let's see, if I put in something like, I don't know if this has more lines coming from the center. No, it's still it's still the same number of lines coming out from the center. It just puts the circles closer together. So that's actually not more lines. And the same with this one. Yeah, it's still the same number of radial lines. Okay. All right, let's try this one. -3 pi over 2. All right, so again, I'm looking at that angle. We might want to change that to degrees. Jade, can you tell me what that would be in degrees, pi over 2?
6 degrees?
60 is pi over 3. Do you remember what pi over 4 was?
That was, I want to say 45.
That was 45. So pi over 2 is twice as big.
So 90.
Right, because the denominator is half of 4. So pi over 2 is 90. -3, 90. All right, Justice, can you tell me how to graph, or at least how to start graphing that one?
You'd go 3 units to the left.
Yeah, this is the first time we've gone to the left. So we're going to go to the left 3. And now everything is, this is like my 0 point. This is where I start from. That's how many degrees I need to rotate. So Katie, how many degrees are we going to rotate?
90 degrees.
90, and which way?
I think counterclockwise.
Counterclockwise because it's positive. So I'm going to be rotating this way. Okay, so I'm going to end up right there. This time I'm going to draw how we got there. We went this way, and then that way. What's another way that I could get to that point besides -390? Yeah?
+3,
+3, -90. Yep. So +3, 3 to the right, -90 would bring me that way. All right. What's another way? Yep.
-3, +270.
So -3.
-270.
So -3 would bring me 3 this way, and then you said -270?
Yes.
Yep. -270 would bring me around clockwise. Just like that. And one more. Hey. If you look at the different combinations we have, we've got a negative positive. We've got a positive negative. We have the negative negative. We're missing the positive positive, which I want to do in a different color. Yeah.
+3, +270.
+3, +270. So there are different ways to get to the same point. If you said, well, what if I went to the right and then went around one time and then just kept going around again and then stopped? Well, that's not really a different way. If you count that, then there's an infinite amount of ways. But the 4 ways are either going to the right and clockwise, to the right and counterclockwise. There's 2. You can go to the left and go clockwise, or you can go to the left and go counterclockwise. There's your 4. Sometimes there's only 3. For example, if you look at a point like here, you can go to the right, but then there is no going clockwise or counterclockwise. In this case, the angle is 0 because it's on the polar axis. You can go to the left and then go this way. You can go to the left and then go this way. So there's 2. You can go to the right and not do anything. There's 3, and that's it. So in that case, there's only 3. But in this case, there's 4. Now, let's look at, you know what, let me just go like this. So you had something like this. And you wanted to know the coordinates of that point. How many different ways can you write the coordinates of that exact point right there? Yep,
One.
just one way. When you're talking about points in rectangular, there is only one possible way you can write the coordinate and have it be correct. In polar, there's 4. So the reason I show you that is because if you do a problem on a test and it is like a matching or multiple choice, maybe I write my answer as 3, 270, but when you do the problem, you get 3, -90. That's the same thing. So you have to understand that your answer is the same as my answer. How do you do that? I think the easiest way is with a picture. Right, you could try to come up with a formula like, all right, well, if I just take this number and add 360, I get that number. Or if I minus 360, I can get that number. And you could try to come up with formulas to do it all, but I think it's a lot easier to just look at a picture. And that's how you want to do it. Any questions on that? All right. That's a negative. We already kind of talked about that. Let's look at this one. 0, 300. Anyone have an idea where that one's going to end up? Yeah?
The middle.
Yeah, it's going to end up right in the middle. Basically what's going to happen there is the radius is 0, and it's rotating in place 300 degrees. So you want to take your point, and you want to spin it 300 degrees, just like that. Right, when we did the test on paper, I could tell if you did that because what I would do is I would look for what I call the SF, the spin factor. So when you put your pencil down and you spin it with a magnifying glass, I could see if you actually spun your pencil, and I could check it. A microscope sometimes really helps. You know what I'm saying? I could check it. So anyway, 0, 300, it just stays right at the origin. Doesn't move. All right. How about 1, 0? If the 0 is in the second spot, is this going to be at the origin? Where's that going to end up? Yeah?
1 unit to the right.
It's going to end up 1 unit to the right. So when the second number is 0, it's going to end up somewhere on this polar axis, either to the left or to the right. When the first number is 0, it's going to end up at the origin. So that goes through pretty much every case you could have. Positives, negatives, and zeros. Any questions in general on graphing and polar? All right, so here's a coordinate. And what I want you to do is you don't have to graph it. I mean, maybe that would be helpful. But I want you to try to write it different ways. Now, I think the easiest thing is going to be if you write this in degrees. It's a lot easier to do the math if it's in degrees. What's pi over 6? Anyone remember what that is in degrees? Pi over 6? Yep.
Like 30.
Yep, good. That's 30. So let's use 3, 30 just to make the math easier, then we don't have to deal with a pi. All right, so here's the 3 different ways I want to write that point. The first way I want to write it, I want to keep the radius positive, but I want to make the angle bigger. Specifically, I want to make the angle between 360 and 720. So what's happening in this one is you're going around an extra time before you stop at the point. I want to know what the angle would be if you go around more than once and then stop. Okay, the second way, now I want the radius to be a negative number. Okay, we did some of those in the last problem, 2 problems. I want the radius to be a negative number, and I want the angle between 0 and 360. And the last way I want to write the point is I want the radius to be a positive number, but this time I want to go in the clockwise direction. I want the angle to be negative. So again, just kind of look at it and figure it all out in your head. It can be kind of hard. I think the easiest thing is take that point, put it on a graph, and then you'll have something to look at so you can see, okay, I gotta go around this much, or I gotta go around that much. Right, so let's put it on a graph. So it's 3, 30. So we're gonna put that point 3 units to the right, 15, 30. So that's where that point is. If everybody has what's on the left, I can make the graph on the right bigger. Everybody have what's on the left? All right, so see if you can figure out those 3 different ways to write the coordinate. And if you get stuck, I would figure out how much it is from there to there. We know that part's 30 to get up to that point. So then you can figure out, you know, what the rest of it is if you want to go the other way. Because you know all the way around is 360. So whatever's left from 30 brings you the other way. And that's one of the answers I'm looking for. All right, so I'll leave that up there for a minute or two and see if you can figure out 3 different ways to write that coordinate. All right, if you get stuck, just let me know. Okay, I'll come help you. All right, so the first way they want us to write the point is with a positive radius. And let's just worry about that first. So if they want a positive radius, there's only one choice. What does it have to be? It has to be 3. Now, they want an angle between 360 and 720. In terms of revolutions, what is that? How many times around?
2.
Between 1 and 2, right? And if it's a positive, which way are we going? Clockwise or counterclockwise? Counterclockwise. So what we're doing is this. Starting here. And you're going around like that. That's between 1 and 2 revolutions. So what would that angle be if we figure it out from that green? Yep. 390 degrees. You don't normally go around more than once like that. They wanted us to, so we did it. But again, that's not normally something you have to do. Okay, next one. They want the radius to be less than 0. That means they want it to be a negative number. So if the radius is going to be negative, it's got to be negative 3. Okay, let's erase this. There's my original point. And you're starting from the x. The angle is positive. So which way are we going from that x to get to the dot? Justice?
Counterclockwise.
We're going to go counterclockwise. So what we have to do is figure out what that is right there. And I think it's easier to figure it out on a picture because you can just look at it and visually see it. Anyone get an answer for that in degrees? How much? 210. Yeah, it's halfway gets you right here. And then you got to go 30 more to get to that point. So it's 210. And the last way they want is the radius to be positive. So what are we going to use for R? How much? 3. Get rid of this. Maybe. So there's my point again. So we're going to go 3 to the right, because that's what they want. But what direction are we going to rotate to get to the angle? Clockwise or counterclockwise? Yep. We're going clockwise because they want it to be negative. It's like we're going to take the long way. Well, we know how much that section is. So how much is that other section? And because we went clockwise, what kind of number? Negative. That's negative 330 degrees. So just a little practice writing points different ways. Any question on that? Last thing for today is how do we take a point that we're learning about now in polar and change it back to a way we were used to working with? How do we get it back to an XY value instead of polar? So in polar, what do we call the two things that they give you? And what's the first part of the coordinate called? That's your radius. And what's the second part? Theta, that's your angle. Now, we're trying to convert that into the system of coordinates we're used to. What do they give you in that system? They don't give you an R and a theta. A what? They give you an X and a Y. So the goal here is to turn a distance from the origin and an amount of rotation into a horizontal and a vertical value. All right, so let's pretend this is our point. If that's a point in polar, you would know two things about it. First of all, you would know that distance. And if you want to think of it, like this, good. That line in black that I just drew is my Y. Yep.
Radius.
That's my radius. And that is my angle. It's the amount of rotation from the polar axis in a counterclockwise direction to get to that point in green. Now my goal is to turn R and theta into an X and a Y. So what shape do you think I can make inside this circle? We've done something similar to this before.
Triangle.
We're going to make a triangle. What we need is a vertical right there. Now, color the two sides. There's one side. And here's the other side. What would the side in green be? Yep.
Your X.
That's my X value. X is a horizontal distance from the origin to the left or to the right. In this case, to the right. X is my green value. And what about the blue? That's the height of my triangle, and that would really be my what?
Y.
That's my Y, right? Instead of telling me how far out you went on the circle and then an amount of rotation, you could tell me the length of the base of the triangle and the height of the triangle, and that would be an XY coordinate. So that's what we have to figure out, X and Y. Let's start with X. Let's say you want to find that, and you know that, and you know that. Anybody remember what trig function you would use? And if you're not sure, think about the two sides that you know. What's R in that triangle? I mean, it's the radius, but what is it in the triangle?
The hypotenuse.
It's the hypotenuse. So there is a certain trig function that uses hypotenuse. And what about x? Not the hypotenuse. Which one of the other two is that? That's adjacent. What trig function has those two sides in it? Hypotenuse and adjacent. Yep.
The tangent.
Tangent is opposite and adjacent.
Okay.
We're actually not going to use tangent today. We're going to use that one tomorrow. Anyone else remember what trig function has hypotenuse and adjacent?
Cosine.
Cosine. Yep. So we're going to use cosine. Cosine is how you figure out the x value of a coordinate when you're converting from polar. You use the cosine. So the cosine of my angle would equal, and then we do adjacent over hypotenuse. X is adjacent, hypotenuse is r. And how would you get the x by itself in that formula?
Times both sides by
You times both sides by r. Yep. So you have r cosine theta. That is how you convert a coordinate in polar to the x value. You take the cosine of the angle and you multiply by r. What are you really doing? You're finding the length of the bottom of a triangle. That's the x value. Now we need the y value. What trig function would we use for the y? Yep, we're going to use sine. So sine would equal. And what would my fraction be on the other side here? Opposite over hypotenuse. Yep. And Gina, what's the opposite in this case? Y. And what's the hypotenuse? R. Yep. So we end up with y over r. And again, the whole goal is to figure out a formula for y. So what would go in that box?
r sine
Yep. And those are the two formulas that you use to convert something in polar to rectangular. You use the cosine to get the x value, and you use the sine to get the y value. I think I write the same thing again here. It's the same formulas. So to convert from polar to rectangular, he'll give you a point in polar. You're going to know the radius and the angle, and you plug those two numbers into the two formulas we just wrote down. Yeah, it's the same formula you just had. Now, if you notice, out of the three trig functions we normally use, which one aren't we using? We're not using the tangent. The tangent is going to be used tomorrow when we want to do the other one. When you want to go from rectangular to polar. Okay, so we'll talk about that tomorrow. All right, so we'll try 2 examples of that, and then that'll be it. Okay, everyone have those 2 formulas? Okay. Now, there is no need to change something that's in radians to degrees or convert anything like that. My advice, leave it exactly the way they give it to you. Change the mode on your calculator. Then the calculator will handle it for you. Okay. All right, so 6 comma pi over 6. You don't have to tell me what the exact answer is, but can somebody tell me what my formula for x would be? Filling in those 2 numbers in those 2 spots. Right?
Would be x equals 6 cosine pi over 6.
Yep. And I know that that pi over 6 is a radian because it doesn't have the degree symbol, so I'm just going to change my calculator to radians when I do this. And what about my formula for y? Yes.
6 sine 5/6.
6 sine pi over 6. All right, let's type it in and see what we get. The first thing I got to check on my calculator, if we're going to do this problem in radians, I can't be in degrees. If I want to do degrees, then I need to make the pi over 6 a third. We talked about that earlier. I think it's better to just keep it as pi over 6. Change to radians. Type in 6 cosine pi over 6. And that gives me about, I don't know if you can really see it, but it's about 5.2, roughly 5.20. So there's my x value, a little bit more than 5 units, right? And now we need 6 sine pi over 6. Oops. 6 sine pi over 6. And that gives me 3. So 6 sine pi over 6 is 3. Right, and just write that as a coordinate. So 5.2, comma, 3. That's how you convert from polar to rectangular. Now, what did I say pi over 6 was in degrees? 30. So 6 comma 30. Let's see. 1, 2, 3, 4, 5, 6. 30. Is there anyone that disagrees that that's not where the point would be? Six units right, and then 30 degrees counterclockwise. Now, what I'm going to do is I'm going to leave that point right where it is, and I'm going to change the background behind it to rectangular. If we did this right, the point should look like it's exactly 5.2 units right and 3 units up. Well, let's see. So remember those two numbers, 5.2 units right, 3 units up. Does that point look like it's a little bit more than 5 units right and exactly 3 units up? Yeah. So just a way I can check the answer on here by changing the background behind it, not really something you can do on paper. But that's exactly where it should be, 5.2 comma 3. Any questions on that? All right, so that's the first part of 5.1. Graphing and converting polar to rectangular. Tomorrow, we'll take a look at, start off by converting the other way. We'll do rectangular to polar. So those are the questions for tonight. Homework again is PDF on Schoology, so you can just check after the examples. You got about 15 minutes, so if there's anything you want to check in with me about, that would be a good time. What's that? I do.